Let's go ahead and continue with where we left off on Monday. We were at the big picture talking about the type of algorithmic analysis that can really help us understand the programs we aim to write without having to necessarily go through all the steps of writing the code, debugging the code, measuring the performance of the code. And again, what I mentioned on Monday still holds true today. The topic of algorithms is its own course or courses, book or books that one would really have to dedicate some time to learn and to study. But gaining an appreciation for some of that analysis and some of the trade-offs inherent in different implementations and algorithms is a valid thing for us to accomplish, even in the very minimal time we have remaining here. And where we left off was kind of this sort of big picture visualization of different sorting algorithms as categorized by their complexity class. This semester, and I've told you it's been fine, and it has been all fine all semester, we've really been working when we've done sorting with either bubble sort or really selection sort, depending on how you order the for loops there. We had that order n squared, or big O of n squared implementation of our sort. Way we kind of reasoned about that on Monday was, well, we have this inner loop of roughly size n, and we have this outer loop of roughly size n. You take those together, you basically have stuff, operations of size n squared. And for the inner loop and for the outer loop, you get to n squared that way. That doesn't tell us exactly how long our code is going to run. We still have to implement it. We still have to compile it. We still have to actually measure the performance of our resulting implementation. But it gives us a way to think about the general scalability of our implementation. May not seem like that big of a deal, our n squared versus our n log n complexity of our sorting algorithms. But as we saw on Monday, as n grows sufficiently large, that can make a significant difference in terms of the resulting scalability. It is definitely true. If you want to sort 10 things, don't sweat it. And probably with modern computers, if you want to sort 10,000 things, probably don't sweat it that much either. But as we write programs and as we want to solve important and meaningful problems, we really can't necessarily cap what a reasonable value of n is going to be in any particular circumstance. Or it's going to be application dependent. Today we write a program that sorts 100 things. Tomorrow we may very well write a program that sorts 100 million things. And when that kind of levels we're talking about in terms of the size of our problem, then it's not just a fancy little visualization difference. The idea of being able to, in this case, recursively subdivide the problem, turn it from an n squared type implementation to an n log n type implementation can make a significant difference in the resulting performance. Again, the whole idea of analyzing an algorithm versus just executing and running, measuring the resulting performance of our implementation, the whole point is we can do that analysis before going through all that effort. Given the constraints, given the size, given the variables associated with our program scope and the problem we're looking to solve, can we have a reasonable high-level estimate of what our critical path is going to be? What is the most performance-consuming part of our program going to be? And as we talked about very briefly on Monday, there's other parts of algorithmic analysis as well. For things like sorting, we kind of just take it as on a level of trust that yes, the sort algorithms will work. The end result will be a sorted array, but it can be very useful to be able to reason and effectively prove in a formal method that yes, if I implement this algorithm, I'm going to get this particular result that I want back out. Again, these algorithms are decades old at this point, but at some point it was useful to be able to prove that yes, if we apply this merge sort algorithm, as we'll talk about here today, the end result is actually going to be a sorted array. We can't just assume that's going to be the case. We have to, at some point, reason about the correctness of what we want to do. Again, this class, we haven't done a lot about that. When we have focused on correctness, it's been, well, if I try a few values, do I get a result that seems in line with what I was hoping for? That's not really correctness. That's testing. And testing and validation is also very critical, but that is also its own separate discipline, its own separate set of books and or classes that one would have a chance to learn about, which is how can I provide a meaningful set of inputs to a program so that I have a higher level of confidence that the end result is correct. That is complementary to algorithmic analysis, which is, can I apply some mathematical and some formal reasoning about the algorithm to be able to determine that the result should be correct? Now, after I've implemented it, validation tells me, can I provide a meaningful representative set of inputs to the program? as well as expected outputs to confirm that my implementation was also correct. We really don't do much of either this semester, as you've seen, right? So we did a little bit of reasoning about our solution, but for the most part, we took it on trust that if you take a standard algorithm, you'll get a standard result. And in terms of testing, we've done just enough to kind of convince ourselves that our code isn't, on its face wrong. We haven't really thoroughly tested things because that itself does require a higher level of rigor in terms of our implementation. You have to think about all the edge cases associated with your implementation. You have to worry about what sort of failure scenarios could be. Eventually, that becomes more important, but for now, we have enough that we've had to learn. We have to learn the basic mechanics of programming and problem solving. So it's okay that we're not so thorough with the type of things we're trying to ultimately prove at the end of the day. So let's look at a couple example sorts and what they do in practice. This is straight from the corresponding Zybook material in that final Zybooks chapter. We have insertion sort. The key concept there is that you have a number of steps, and at the kth step, you put the kth element in the correct sorted position. That's not the same as our bubble sort, although it sounds kind of similar, and ultimately it's two nested for loops, so you get very similar type of performance. In our bubble sort, after k steps, we have k elements sorted. In our insertion sort, after k step, we have the kth element in the correct sorted position. So that's not exactly the same exact thing, but ultimately you have a subset of the array that is sorted, a subset of the array that is not sorted, that is unsorted, and step one is to determine what is my value of k, what is my current value that I'm interested in, and then I have to determine, I know it's going to go somewhere into this sorted array, do a linear search, determine where it needs to go into that array, determine which one is it greater than, which one is it less than. Those are the two indices that this new item needs to fit in between. It's called insertion sort because now it's actually getting inserted over. That actual implementation, at least given our C programming background, would be very annoying. If it was just a statically allocated array, we'd have to do a lot of copying. If it was something like a linked list, it'd be much easier to insert things in the correct location in a linked list just by manipulating pointers. But either way, there's some manipulation of the input values to get this new value in that correct location, and then we just move on to the next one. So for each value of k, take the kth element that's next in our array, put it in the right relative location. So k by k, we wind up having that many values correctly sorted. By the time k is equal to n, or k is equal to the length of the array, every single element has been placed where it needs to go. The end result is a sorted array. Merge sort is our first example of the n log n type algorithm. It also ties in, I think, pretty directly to some of the recursive things we were talking about last week, because it's also a divide and conquer style of strategy. The big picture with merge sort is that we can sort a larger array by first sorting two subarrays. It's kind of like the palindrome. I mean, we're not solving the same question there, but kind of like with the palindrome, remember our divide and conquer there, right? We can determine if the whole string is a palindrome by determining if the substring is a palindrome. And recursively, keep determining if the subsequently smaller substrings are also palindromes. Eventually, you get to the base case. The base case is one or two characters in the string. They're either equal or they're not, and you can work your way back up from there. Merge sort is doing something quite similar. Again, it's not determining if something is a palindrome or not, but it's saying, given this large array is sorted if the subarray is sorted. Consequently, that subarray is sorted if its own subarray is ultimately sorted. Now, unlike determining if something is a palindrome, it either is or it isn't. We're returning a true-false value here. Here, it still has to do a little bit of work, which is I have to ultimately sort the values. It's not determining if it's sorting. If it is already sorted, it is actually sorting the array. So then there's two sides of it, or two steps of it, that makes it a little different than our previous recursive implementations. So there's the recursive part, the divide and conquer, and then there's the so-called merging part, which is once we get elements all the way down where the length of our array is just of size 1. Again, just like in the palindrome, we get down to where our string is of size 1 or 2. In this case, we get down to where our array is of size 1 because we've been recursively dividing. It was of length 16, then we look at 8, 4, 2, eventually get to 1. Once we pop back up, once we return from that recursive call, we don't do so blindly. We then merge those two subarrays together. And it turns out that process, which is still sorting, give me two values that I'm merging together and determine if they need to be swapped or not. So we're still sorting there, and then give me two arrays of size 2 and merge those two together, that process is itself just a linear operation. It's still a lot of comparisons, check this element versus this element, swap them if need be. But because if we can guarantee that each individual subarray is sorted, the process of merging them together becomes a linear and not a quadratic operation. That is all hand wavy. You take an algorithms class, you prove that very thoroughly. For our purposes, assuming that that is correct is sufficient. And then in terms of the resulting performance of that, the reason it's order n log n is because the step of doing that division part, going from 16 to 8 to 4 to 2 to 1, well, we can count that. That's logarithmic, right? We're splitting in half each time. That part is log n in terms of the runtime of splitting things up. Merging things back together is only linear. It's only order n, big O of n, because we just have to kind of look at each element once and check, do I need to swap or not? Multiplying those two steps together, we get order n log n. We get a significantly better performance than our bubble sort or our insertion sort type of sorting. I think it's best explained not looking at the code yet, because the code does ultimately look like this kind of recursive call. There's a lot of different merge sorts you'll see out there. The textbook version looks quite a bit different than my version, but they're all doing something pretty similar, which is take my input array, handle the left-hand side, handle the right-hand side, so split it effectively in half, and then do that merge operation together. So it's a recursive call, but there's actually two functions associated with it then. There's the recursive call. Merge sort is going to call itself twice. Call it on the left-hand side, call it on the right-hand side. That's going to be recursive all the way down until you have arrays of size 1. And then once you finally are done with all that merging, or all that sorting and subdivision, then there's a separate function call that's going to then combine those two sub-arrays together. It's a little messy. I think it's easier to visualize what's happening versus trying to look at the code first. So if this is my input array of length 8, I'm going to split it in half. And with pointers or just subarrays, that doesn't really require any effort, right? It's just calling the function with updated pointers, and or you would have to pass it like a start position and an end position. But either way, that's what would happen here. So going back to the code, we have an input array. The first thing we do, assuming the length is not already equal to 1 or less, we call merge sort on the left-hand side and the right-hand side. Give me the first 4 elements and the last 4 elements. Cut it in half. It's recursive. We got our Matryoshka dolls all the way down here, right? Technically, and I don't know if I actually animated this properly, technically this first merge sort call is the one that gets called first, right? There's 2 lines of code. They're sequential from each other. So we call this top level merge sort. This first merge sort is what gets called first. And in terms of the control flow, the program flow, there's no parallelism here. I mean, there could be, but there isn't any actual parallelism going on here. So that merge sort gets called first, and consequently the left-hand side, yeah, and I didn't visualize this correctly, unfortunately, but this left-hand side is what would get partitioned next. And then that left-hand side is what would get partitioned next. So technically, like the animation order here isn't quite correct. But logically, it's still doing the correct steps, just not exactly in the right order as it would happen in practice. Start with our length 8 array. We wind up with 2 length 4 arrays. We constantly wind up with 4 length 2 arrays. And then ultimately, you can still think of them as arrays. We have 8 length 1 arrays. We do all the subdivision down from 8 to 4 to 2 to 1. Again, in practice, it would be a depth first search. We would go here, then we would do this, then finally we would do this side. But it's still, the end result is the same in terms of that subdivision that happens here. That is the divide part. We haven't done any conquering yet, right? Because we've divided it all the way down, but we haven't really done anything. We haven't sorted anything. That then is that second step of the implementation. And I have to go back to the code here to show that once we've all the way split things up, those recursive calls would ultimately return back. They'd be done. We'd have merge sorted the left-hand side, merge sorted the right-hand side. To actually finish this function call, we would then call merge. That is the step that's going to combine the left-hand side and the right-hand side and do so in a way in which it'll maintain correct order of that left-hand side and right-hand side. So the subdivision doesn't really do much. It's kind of just pointer bookkeeping. It's setting up the rest of the sorting that's going to happen. Now when I finally have divided all the way down, I have a step that's now going to combine the left and right-hand side. That's where your swapping is ultimately going to happen. I'm going to combine 7 and 2. At that point, I actually determine if I want it in ascending order. When I combine those two, I'm going to actually reorder them so they're in correct relative order to each other. Is this one greater than this one? If so, swap them. Basically is what's happening inside that code. That's for the first and the deepest level of our merge operation, and we're just going to continue doing that. And it just so turns out that because if the left-hand side and the right-hand side are ordered relative to each other, that the whole thing isn't ordered yet, but this side is ordered and this side is ordered, merging them together is just a linear operation. You have to kind of check, which one is currently greater than the other and copy that into the resulting array. So merging 2 and 7 with 4 and 8 is easier than sorting 7, 2, 8, 4. And so we do that merger step. We get a left-hand side and a right-hand side that are both ordered relative or sorted relative to each other. And we have that final merge to get our resulting sorted array back out. Let's look at what that looks like from a code perspective. I didn't want us to code it from scratch. I don't know if we would have learned very much more as opposed to just looking at an existing implementation of it. This is effectively the textbook version of the merge sort implementation. Just a couple things that are maybe a little bit different here. I wanted to also, in addition to showing merge sort, just kind of show the performance of our bubble sort versus our merge sort. So, and actually this code can do either. So given our program name, pass in a value of n, and then also pass in the value of b or a value of m to do bubble sort versus a merge sort. And then because I also wanted to kind of time the performance, you will see a version of this in all sorts of different kind of timekeeping code out there. There's existing structures in the C standard library that allow us to more precisely keep track of system time and to do some very minimal mathematical manipulation, basically a start and stop watch kind of calculation here. So we define two variables of a built-in structure called time value, call them start and end. There's more than one function you can use for this purpose, but the very common one people use is called get time of day. Those of you playing around with like clocks or timers or anything like that in your programs may find value in using those functions. They have microsecond granularity, so they might be overkill for a lot of what you want to do. If you just want a single second timer, you're probably going to be okay. And similarly, if your second is actually 1.05 seconds, nobody's going to notice, nobody's going to care. But if you really do need accurate timing, well, there's a lot of things that involve, taking these timestamps and determining, well, this block of code, and you can't quite see it, but the block of code in between line 128, when I call get time of day the first time, and line 138, where I call get time of day the second time, it took this many milliseconds or microseconds or seconds. Consequently, if I want to have a timer that's going to update like a second clock or something, I should use that information and maybe sleep the remainder of the time. That's if you want a very accurate, you want to hit 60 frames per second in your video game, and so you have to determine exactly how much time it took your frame to process and sleep the remainder of the time. For a lot of your things, if you're doing Minesweeper and you just want a 1 second timer ticking down, if it takes 1.1 seconds, nobody's going to care, nobody's going to notice. So you can just sleep for 1 second at the end. But this is a way to get more precise timing information. So there's not a lot going on in the code, but we hit our time start. We then, depending on what the input was, we either call our bubble sort or we call our merge sort function. And then there's just a little bit of a calculation given that structure encodes both the elapsed time in seconds as well as elapsed time to round up in microseconds. You just do a little bit of a multiplication. Multiply your elapsed time in seconds by 1,000,000, add in the microseconds and subtract it. So take my end timer, subtract my start timer. That gives you a resulting pretty accurate elapsed time in microseconds based on your system timer. So we just have that there so you can kind of see as we run this. Here's how long bubble sort takes. Here's how long merge sort takes. And we have our actual bubble sort implementation is exactly the way it was before. Now we have our merge sort implementation. Takes in our array, takes in, for the current call, what is our left index, what is our right index. Other implementations you may see may just explicitly use pointers to encode that information, but for now, left index and right index. What is the start of the array? What is the last index in the array? So when we call it the first time, we call it with 0 and then n minus 1 for the final index. If our length is 1, we're done. We don't have to recursively call anymore. Otherwise, calculate just using our integer arithmetic what our current midpoint index would be. And now recursively call merge sort twice more. If m is our midpoint, L is our left, and R is our rightmost index, we could have broken ties a couple different ways, but take merge sort and call it on L to M, the left-hand side of our array. Now call it on M plus 1 to R, that's the right-hand side of the array, and then merge those resulting results together. So again, this is the divide part, but it's not really doing any conquering yet, right? It's just subdividing up the problem from size n to n over 2 to n over 4 in that logarithmic style. And then that separate function called merge is the one that's doing that relative sorting, which does turn out in terms of complexity be easier. If I know the left-hand side is sorted and I know the right-hand side is sorted, merging them together can be done in one pass, in one for loop across both the left-hand side and the right-hand side. And that's what that merge function is attempting to do here. This was completely unnecessary the way I implemented this, and why did I do it? I don't recall. I did it a few months ago, and when we write code a few months ago, and in the past, we kind of forget what our thought process was. But in this case, the way I implement this is to do dynamic memory allocation and to copy over the left-hand side and to copy over the right-hand side. It's not necessary that you do that, but that's what I did here. So given an L, left index, an M for middle index, and an R for right index, that defines two subarrays of size n1 and size n2 as given here. So I said, let me allocate those, and let me explicitly copy them over into subarrays, one called L and one called R. That is not necessary. Nor does it necessarily make the rest of the code that much easier to understand, but now at least it's being more explicit that this is the left-hand side, this is the right-hand side, one is called L, one is called R. I could have done it with a pointer, it would have been also just one line of code, but this is how I did it, so that's fine. So allocate an array for the left-hand side, allocate an array for the right-hand side, and then explicitly copy it. And then that merger step, the code looks a little bit funky, but the big picture concept is I just go element by element and maybe opening up the slide and perhaps looking at the final merger is a little bit easier than some of the smaller mergers that we have here. We have the L array here, we have the R array here, and I know I have to combine them together, and we basically just keep track of two separate indices, which is how far along am I in the L array as well as in the R array, and compare them to each other. Compare L of 0 to R of 0. Well, R of 0 is smaller if we're sorting in increased order. So copy in R of 0, increment this pointer here. Do it again. Compare L of 0 to R of 1. Well, L of 0 is now the smaller one. Copy that in here, increment the pointer. Compare L of 1 to R of 1. Copy the lower of those two over. That's exactly what's happening in this code here. As we iterate through an index for both a left array, which is called I in this code, and for the right array, which is called J in this code, compare them to each other, copy one of them over back into the original array. And then there's just a little bit of extra cleanup code because we're going to finish one of these subarrays before we finish the other one. Copy the rest of the other array over. If we finish the right array earliest, copy the rest of the left over. If we finish the left array earliest, copy the rest of the right array back over. So we're going to call it. First, just for comparison, we're going to call bubble sort with 100 elements. And it's called N. I did it backwards. N first and then B. So 100 elements and call it with bubble sort. We get 14 microseconds. Now when we compare it, we call merge sort and we get 11 microseconds. And again, as I mentioned, well, was it worth it, right? Was it worth all that extra effort? I did make the merge sort slower than it had to be. An algorithm person would tell you that all of this stuff, all the malloc, all the copying over doesn't change the complexity because it doesn't. Those are all linear operations. So it's order n log n plus n. Well, so it's the same. It doesn't actually slow it down any. In practice, those things take actual instructions on your CPU, so it does slow it down in practice. But then the end result is 14 microseconds versus 11 microseconds. Is 3 microseconds critical for you? In this class, it never is for the most part. In practice for you, it really depends. Depends on what your constraints are, whether there's a lot of important things you need to get done in those 3 microseconds. You will write code at some point in your life in which 3 microseconds are critical, and you have to think very carefully about every microsecond in your code. But we can kind of, although I'm not going to be able to plot it very easily here, we can start to run it with larger values of n just to see the result, and hopefully to kind of get a hand-wavy feel for the complexity difference here. That's now running it for 1,000. Okay, now the merge sort's starting to get a little bit faster than the bubble sort. We could have, I sure did. Thank you. Now it's significantly faster than that. Let's clean up that mistake. Okay, significantly faster. Okay, it's not. There's a lot of non-determinism. This is a cloud computing environment running other applications. You're not going to get the same exact result running your program, not at the microsecond level granularity at least, but roughly the same. We can keep going. Again, that's in microseconds, so it's still pretty much a blink of the eye, right, in terms of running on both algorithms here. But you can start to maybe see the kind of quadratic growth of the bubble sort that eventually we're going to get into some trouble with our bubble sort. We're not quite, I would say, in trouble yet, but we're only sorting 100,000 elements here, and now it actually has kind of a measurable runtime associated with it. And it's just really awkward to have to wait for this to finish. But it shouldn't be too bad. It should just be a matter of seconds. Okay, good. That was in microseconds, but then that's 18 million microseconds. So 18 seconds it took to run a bubble sort. 100,000 elements isn't nothing, right? That's, I mean, it's 100,000, but in terms of like the type of data one has to process on a day-to-day basis, it's really not that much. Any microsecond predictions for 100,000 merge sorted elements? I don't know, I can't do the math in my head either, but it's still significantly faster, right? 12,000 microseconds, and probably, we can't run this for bubble sort anymore, right? It would really bog us down, Replit would get mad. But as we keep running merge sort, eventually it's going to bog down as well. It still scales at that size n log n, so given a sufficiently large n, we won't be able to do merge sort in enough time, but it scales quite a bit better, right? So even running merge sort now with, that was 10 million elements. Let's get greedy. Let's run it with 100 million elements here. And I'm pretty sure running merge sort with 100 million elements will still be competitive with running bubble sort with 100,000 elements. And that's a significant difference. Good question. Certainly can, because there is that overhead associated with it, right? And I actually posted an article about that in our, no one reads our Discord anymore, but about like, when do you ever want to use bubble sort? And the answer is probably never, but there's advantages. It's simple, it's straightforward. You can write it in a few lines and not have to think about it ever again. But for really small arrays, it may make sense to do, bubble sort. I don't know if the way I wrote this, if it's going to make a difference, but let's try it. So we did see for 100 million, technically it's slower than the bubble sort, but it's competitive, right? 100 million at merge sort is roughly the same as 100,000 at bubble sort. But if instead I wanted to run bubble sort on 4 elements, I mean, this granularity is probably not good enough for me to see the difference. It might, in fact, be faster to run bubble sort on 4 elements than merge sort on those 4 elements. So there are all sorts of modern sorts. That wasn't meant to be a play on words. There are all different varieties of modern sorting algorithms that kind of take that into account. That as the array is really big, do something n log n, or even better if you can. But then once the array gets down to a manageable size, right? As we do divide, eventually the size of the array, even if we started with 100 million, eventually the size of the array is going to be 4 at some point, right? Eventually then it might make sense to kind of switch on over. So actually bubble sort the remaining array and then use merge sort for the rest of it, or some hybrid combination of the same. Ultimately, I think most modern sorting algorithms are more complicated than these kind of textbook versions. They tend to take some knowledge of the data into account. And when I look at some of the more recently published sorting algorithms, they try to do very clever things like first analyze, determine how unsorted the array is in the first place. And if there's whole stretches where it's actually already sorted, do something more clever than just do a naive kind of bland version of quicksort or merge sorting. It's some hybrid approach. Because ultimately there, when you're writing a sort for a standard library that's going to be used by hundreds of millions of people, The goal is not to have the most beautiful looking algorithm, but the one that's going to guarantee really good performance in all sorts of different scenarios. Other merge sort questions. We also have quicksort, which is in some ways quite similar, but the implementation looks quite a bit different. It's also divide and conquer. It's an interesting one to study in an algorithms course because unlike merge sort, if I just go back to this picture, which is kind of consistent in terms of what happens with it, cut it in half, cut it in half, cut it in half. In quicksort, we're also dividing, but we do so based on a particular value in the array. And so consequently, it turns out if you take an algorithms class, it's a little bit harder to reason about the performance of a quicksort because it does depend on how random the array is and depends on the choice of that pivot element that you choose. But otherwise, it's doing something very similar. Instead of just cutting in half, it's the quicksort approach is pick an element. And some textbook versions just basically say pick any element. You may want to pick one that's like the median value or something like that, but just pick any element. In this case, we're literally picking the first element in the array. The Zybooks has an example where it picks the very last element in the array. You could pick an element that's literally in the middle of the array. It doesn't really matter, but you pick an element, and what you then do to do your division is to determine, with a pass over the array, split the array into two subarrays again, based on whether the elements in the array are less than the pivot, or less than or equal to the pivot, or the elements in the array are greater than the pivot. So the choice of the pivot ultimately matters quite a bit in terms of the complexity, but there's a lot of that kind of formal analysis that can be applied. And the end result is, in general, there's some worst case performance of quicksort, but your average case performance, you're pretty much likely to get something very competitive with a merge sort type of implementation. We take our value of 5 here, we then go through the entire array and put things into two buckets, less than 5, greater than 5. And you can kind of see where we go from there, right? Then we subdivide, pick another pivot for the left side, pick another pivot for the right side, put it into two more buckets. So we start with 1 bucket, then 2 buckets, then 4 buckets, then 8 buckets. We get the same kind of result here, right? Which is as we continue to subdivide our arrays, our end result is everything is ultimately kind of sorted relative to the pivot elements that we've selected. Not in the same way they are with merge sort, where only the left-hand side is sorted and the right-hand side is sorted. When we do our quicksort sorts, they're all going to be completely sorted relative to each other because we've actually moved elements into the left or right-hand side, depending on which side of the pivot they fall into. There's all sorts of different ways you can also implement quicksort. I think I'll kind of just quickly just pass over this here, but the idea is you determine a partition index. What is the value I'm interested in actually grabbing? And from that partitioning, you then just do your subdivision. You do your divide and conquer at that point. So it even kind of looks sort of similar, the code for quicksort, as the one for merge sort. It is, again, doing something different. It's actually checking the values and determining whether it needs to go on the left or needs to go into the right. And so in that sense, whereas merge sort was recursion, recursion, then merge together, combine back results, here it's kind of the opposite, split results, then recursion, recursion. But I think at a high level, you can look at that implementation and say, yeah, it should be pretty similar. I'm cutting it in half, doing a left half and a right half. The end result is something based on how I did the partitioning, that by the time I get all the way down to buckets of size 1, the end result is I have a sorted array back out. I don't have to merge anything back together. Now, having said all that and having a bunch of different examples for how to do these different sorts in C, my advice, and this doesn't apply to C, this applies to any programming environment you find yourself in, is if you find yourself implementing a sort, like for a real task, not for a classroom task. Yes, if it's a homework assignment, do whatever the homework assignment requires. But you're on your internship, you're in a real task, and you have to sort this data as part of your program. Just like with all of the other kind of standard library stuff, yes, we could write a function that does copying one string to another string. It's just unlikely our implementation is going to be better than a standard library implementation of the same. Checking all the values and converting them from uppercase to lowercase in a string. We could write that ourselves. It's not that hard to do. There's little reason to believe our implementation is going to be either more correct, more better performant than a standard library implementation. The same holds true for sorting algorithms as well. in your choice of library, framework, programming language. If it's something invented after the year, I don't know, 1980, it's likely to have some sort of standard approach to doing sorting kind of baked into either the language or kind of common standard libraries provided, supported with that language. And the standard C library provides that as well. There's a function in the standard C library called qsort, which, despite the name, does not require it be implemented via quicksort, but it can be implemented via quicksort. You don't necessarily have any guarantee how it's being implemented under the hood, but I think a reasonable assumption one can make is that if part of a standard library for a standard supported platform that you're executing your code on, it should be pretty decent. It should be probably as good, maybe better than what you'd be implementing yourself. What makes this a little bit harder to use than some of the other standard library functions is because sorting something is not well defined, right? When we have been talking sorting all semester, we've been sorting in increasing order, but that's not the only definition of sorting. Why increasing order? Why not decreasing order? Why not any kind of arbitrary sorting by first name, by last name, by GPA, whatever sorting we want to necessarily do? The term sort itself applies a strict ordering of the resulting values in our list or our bucket or our array. It doesn't really define what that ordering definition is. So as part of using the qsort algorithm, and this is why the syntax looks pretty whack, I think, compared to other functions we've been using all semester long. As part of that, you yourself have to define what does it mean to have that relative ordering. So what you define when you call this, and I hope at this point we've gotten a little bit better with some of this standard library syntax. It's not all complete, voodoo to us at this point. Void star pointer, what do we think that's going to be? Yeah, the data. That's our array. Size t count, do we know what that's for? Yeah, and we have to be a bit more precise, but yes, the length of the array, or the number of elements, the count of things in our array. For a lot of these functions, including some of the memory allocation ones, we've also really need to know how many bytes is each item in our array. If we're sorting ints, it may be different than sorting doubles, which may be different than sorting custom structures that we ourselves have defined, and this function has to be able to support all of those. And then that final input is pretty nasty. It is a definition of a pointer to a function that we ourselves then have to provide that takes in two constant pointers and returns a value determining whether value left is greater than value right or if it's not. So we provide that function. We have to implement then that function, and then we call qsort, and our end result is our array is sorted based on whatever we defined that function to be. And to be able to do that, we really do have to look at that definition. Again, this is just straight from the slide, the function definition. We have to actually look at the comp part, that final input, that comparison function. And it's definitely okay if you have to look this back up when it comes time to actually implement this yourself. Comparison function, which returns a negative integer value if the first argument is less than the second, a positive integer value if the first argument is greater than the second, and 0 if the arguments are equivalent. What does less mean? What does greater mean? What does equal mean? You get to define that. So it depends on whatever data you are interested in sorting and how you're interested in sorting it, you get to define what that is. If today you want to sort by GPA, you call it qsort with a function that defines the relative GPA scores to be the sorting criteria. If tomorrow you want to sort by last name, you still just call qsort, but now you set in your function that I want to sort based on the alphabetic, last name here. And the signature of the comparison function should be equivalent to the following. You can call your function comp if you want to. That's fine. If you only have one comparison function, you have to call it something a little bit better. If you're going to have 20 comparison functions, it takes 2 pointers to an individual element. And based on how you want to do it, you determine whether we return positive, negative, or 0 from that function. And if you get it backwards, I returned a negative integer even though it was great. The first argument was greater than the second. It's not the end of the world. Your array will just be sorted in backwards order, and you check that, you confirm it's backwards, and you just swap the function, and your life is pretty straightforward. I call this qsort fun. Fun is relative. I don't really know necessarily if this is fun or not. This still includes all of the All the other functions for bubble sort and for our merge sort does not include quick sort, but we include as an option where we can pass q, and it'll call q sort on those. So it takes as input the pointer, the values we actually want to sort, the count, the number of things we want to sort, how big each thing is, in this case just an array of integers, and then the actual name, which ultimately be a pointer to that function that defines that actual comparison. It's called my comparison function. Let's take a look at an example of my comparison function. This is straight from the documentation here. Takes in a value a pointer to a value A, and a pointer to a value B. You get to determine, you write the code, what should we interpret that as? So usually the first two lines of your comparison function is, given A, I want to cast that void pointer as an int pointer, so it's now pointing to an int, that address that's been provided, and I actually probably care about the actual value of that integer, so I want to follow that pointer. So give me the value of A, and give me the value of B. In this case, I was just messing around. Sort based on how close each number is to 50. We could do that. That's kind of arbitrary. We could also just sort based on which value is greater than the other. So we could just return, we set result is equal to int A minus int B. And it's possible I have that backwards. Let's look at the documentation again. Returns a negative integer if the first argument is less than the second. That would return a negative integer. So if A is less than B, it will return something negative. If A is greater than B, it'll return something positive. Otherwise, it'll return 0 if they're equal to each other. Let's make sure our bubble sort is still bubble sorting. Our merge sort is still merge sorting. And now we try our Q sort. Again, the temptation is to assume it's implemented via a quick sort, but we have no actual guarantee if that's the case. And it seems competitive with the merge sort, but let's try it with 1,000,000 elements. I have not tested this. I don't know entirely how this will go. It looks like it's a little bit more inefficient than doing the merge sort, but what you gain is a couple things. First off, you've gained a sort via writing just a few lines of code, right? Qsort is implemented elsewhere. You've also gained a much more flexible sorting mechanism by which you get to sort based on your own determination of how you want these values to be sorted. I don't know why I care about how close each number is to 50, but we get roughly the same performance via a completely different sorting decision mechanism there. We can then, if we choose to, print the actual array. We probably don't want to do that for 1,000,000 elements, but if we do that for, say, 1,000 elements, this will be our last thing here today. How did we generate the elements in this example? Rand mod n. So 1,000 elements between 0 and 999. And we want to sort it based on this arbitrary comparison function, which is how close, what's the absolute value of 50 minus int A and the absolute value of 50 minus int B? What's it going to print out here, do we think, for the array? 1,000 would be the values that are furthest from it. If we're doing distance B minus distance A, it should print out a whole bunch of, yeah, you're right, 999, so the highest possible values. I had that backwards. And then our close values to 50 near the very end of the array. Why would we want this? I don't know. If you have some application that requires you take the data and you sort it based on some arbitrary condition, you're changing 1 or 2 lines of your code. The rest of your code doesn't really have to change at all. Let's leave things here for today. I did have an example in which we were going to sort all the words in the dictionary by the length of each word in the dictionary, and I plan on taking a poll to measure the excitement level for that exercise. So stay tuned on Discord for that poll, and I'll use the results of that to influence what Friday may or may not be. Thank you.